Hi, in this video we're going to continue building a robot for our robot simulator. We're going to try and do the agitator, and we're going to try to create the ball shooter, create state machines for both of those. It is now January of 2019, so we've gotten our new software. We are now in FRC 2019. And I've done some investigation and see that the 2018 and 2019 software in simulator are identical. I'm not able to detect any differences at this time. So any code that you've written in the 2018 should port over very easy to 2019. And I can demonstrate that by copying the demo 4 code that I wrote in 2018. And then we can open up this folder and open our project. And we can see that it opened up fine in 2019. If we open robot main, so now we have our demo from demo 4, and we will begin to build the agitator. So before we get started, I want to do a review on timing, because we're going to be doing some timing in our 2 state machines we're going to build. So I'm going to create a new VI and have you kind of just watch. I'm going to create a while loop, and I'm going to create a stop to that while loop, control off of that. And I'm going to use the random number generator here to kind of represent a sensor that's generating data for us. And I'm going to wire that to a tunnel, and I'm going to set this to indexing. So it's going to build an array of data for me as I run this loop. Okay, and we have no timing of any kind right now. And just kind of as a reminder, I'm going to create an indicator here off of our array so that we can see it on our front panel. So this is an array of random number generated data. And then I'm going to put a vertical scroll bar on this as well. Oh, another thing I'm going to do is I'm going to get the size of this array to see how big it gets. So I'm going to get array size, and I'm going to create an indicator off of this as well. And then go back to my, so this is going to tell me the size of the array. I'm going to make this a little bigger because it's going to be a big number. All right, so the time, I'm going to hit go, and then I'm going to quickly go over here and press stop as fast as I can. And let's see how many times we generate a random number just for me going from start to stop. So start, stop. All right, so you can see just in that time, which is not even a second, I generated 38 million, over almost 39 million random numbers, right? So there's a way we can slow the loop down. Say we only want to run the loop 10 times a second, right? So remember data flow, if we put a wait timer in here, and I make this wait timer 100 milliseconds, that means that every 100 milliseconds this will just stay here, wait, and then release. So now I have basically 3 things in parallel. I have a wait timer, I have a random number generator, which takes less than microseconds, and then I have a stop, which also takes less than microseconds. So all these 3 things are happening in parallel, and the while loop cannot finish its iteration and go to the next iteration until all 3 of these things have completed. Well, this one takes 100 milliseconds, so it's definitely the slowest of the 3 parallel operations. And so we are limited by how fast this one can go. All right. So again, we're going to run it, and I'm going to try and stop it as fast as I can. So we're going to start, stop. So you see that time I was able to do it, and we only got 11 iterations because this loop could only run once every 10 times a second. Okay, so that's called execution timing. And that means that we are basically slowing down or timing execution. We're slowing down execution. The other type of timing is called software timing. The software timing doesn't inhibit execution. It just tells you what the current value is and compares it to a previous value. So say we wanted to stop this loop after 5 seconds. Okay, so we could put 5 seconds in here. All right, but we want to still sample at 10 times a second, but we want to stop the loop after 5 seconds. So putting 5 seconds here forces our random number generator, or sensor in this case, to only operate once every 5 seconds. Okay, we still want to operate 10 times a second. So what we can do is we can go to our timing palette and we can pull in our get time in seconds. And what that does is it generates a timestamp. And I'm going to bring up Control H and just hover over it so you can see. So this returns a timestamp, but actually in the back, underneath is the number of seconds that has elapsed since 12 a.m. of January 1st of 1904. And if you take this number and convert it to a double, it will be the number of seconds since 1904. So that if you ever want to do that. But what we usually do is we compare one timestamp to another. We either subtract them, and that gives us the number of seconds that has elapsed since one time to another. So if we put our timestamp generator outside the loop, this will be the time close to the time that the loop actually started. And then I'm going to do a control drag. If we put a timer on the inside of the loop, this will constantly give us the current time of this iteration. And if I subtract this time from my start time, that'll tell me how much time has elapsed inside of this loop. And then I'm going to subtract these two. So I'm going to grab a subtract. I'm going to subtract my current time from my start time, which will give me my elapsed time. And then if my elapsed time, I'm going to grab a greater than or equal to, is greater than or equal to, create a constant here, 5 seconds. And I want to stop my loop. So I'm going to insert an OR gate here. So I either want the stop button or I want this greater than 5 seconds to be true. So I'm going to insert an OR loop, an OR gate. So I'm going to right click, say insert, go to the Boolean palette and say OR. Okay, so now I would predict that if we're getting samples at 10 times a second, and we're waiting for 5 seconds, we should get about 50 samples here. So again, all this is doing is reading the time, the current time on our PC clock, and subtracting one time from another to determine how much time has passed. And these VIs do not block. They get their time very quickly, so they're not an execution timing. They're called software timing. So you can see in a LabVIEW application, you kind of need both timings. You need this one is to help you slow the loop down so it doesn't waste a lot of CPU and resources just doing something super fast. And then you need this timing to kind of tell you when time has completed without slowing down unnecessarily other parallel functions in your BI. So let's run this. So we're predicting we should get about 50 cycles before we stop. About 51. And I'll do it again. I'm going to create an indicator here so you can see the elapsed time. Here's our elapsed time, and we'll run it again. You can see it's subtracting the current time from the start time, and when it gets to 5 it'll stop, and we get about 51 samples. So if we go to our state machines and we see where we're doing timing, let's open our intake, the one we did here for demo 4. We can see that here our target time in milliseconds. This is where we're using our execution timing to slow our loop down, and we set that value here, our target time. So we're going to try and run this loop a maximum of 50 milliseconds per iteration. And you see that the template allows for looking at the current time, so we store that in our cluster, and we also store the previous time. So here we can actually use software timing to tell us how fast our cycles are actually running. When we do our agitator and our ball shooter, we're going to add more timing where we're going to read the current time and save that as our start time, and then later we're going to compare after each iteration we will continue to fill in the current time, compare it to our start time to tell us if how much time has elapsed, so we can make decisions on how much time has elapsed since we came into a certain state, or if our servo is in a position, or if we've let the wheels for the shooter spin up. We're going to use timing for all of those different functions. Okay, so let's begin building our agitator. So I'm going to close down my intake loop and time tasks. We're going to get to the project. So again, if you hit Control-Shift-E, opens our project up, and I am going to open my template code, my system templates, and we are going to make a new actuator. And then I'm going to start to speed up the video here until I get to another talking point. Okay, so we've created our actuator library by copying one of our actuator template, and I placed it in the agitator folder inside of the systems folder, where we've put all our other systems that we've built. So the first thing I do is I build some type of state machine. So previously I did it using LabVIEW objects or decorations. In this case, I've built the agitator state machine using Google Documents, and it's pretty nice because Google Documents has these arrows, so as you move things, the arrows will follow. It makes it a little nicer than trying to use the LabVIEW decorations. But you can use whatever you want. You can use pen and paper, whatever you need, but I would really recommend that you kind of draw one of these state machines before you get started, so that you can kind of map out all the things you need to think about when you start coding. Okay, so our agitator is basically just going to sweep left and right at a specific speed that we comes in from the I believe it comes in from the dashboard. Some sweep speed is set, and we want to sweep from 0 to 170 degrees, which is the range of the servo motor that runs the sweeper. We want to sweep from 0 to 170 degrees in the amount of time specified. So we have a startup state and a shutdown state, like all of our state machines do. And then right from our startup state, we go right to the off state. All right. In the off state, we basically just sit here and we watch our commands. So we have a command to disable. If our command is set to disable, we continue looping here, coming back to the off state. If our command is enabled, then we go to our sweep right state. And in transition between off and sweep right state, we save our start time and we save our start position. Okay, so what we're going to do is, based on the time and our position, we're going to calculate each iteration. A new time will come up, and we'll take the time, subtract our current time from our start time, and then we'll calculate how much time has elapsed. And then as we have a sweep speed set, we will multiply that by the time set to tell us how many positions or how many degrees we need to move our servo. So our servo runs on position, and so we need to set the position each time. And so over here I kind of ran through the calculation. So if we're decreasing our position, which means that we're sweeping left, we take our new position is going to be equal to the start position that we saved here minus the degrees to move. And the way that we calculate here, degrees to move equals our sweep speed in degrees per second times the current time minus our start time. That tells us how many degrees we should have moved in this amount of time, total amount of time. But we don't get our speed in degrees per second. Our sweep speed is given to us in sweeps per second. Okay, so we have to take our sweep speed is going to be equal to our agitator speed in sweeps per second times 170 degrees per sweep. That's what our servo, if we look in our documentation, that's what our servo says is an entire sweep is 170 degrees. So we're going to use all these formulas to tell us what our new position should be. And then if our command is enabled and we haven't reached our full sweep position yet, we do these calculations and we set our increase position, set our new position. And then as long as we're enabled and we're less than 170, we keep sweeping right until we get greater than or equal to 170, and then we grab a new start time and a new start position, and we begin to sweep left. And instead of adding the position, we subtract position from 170 until we get to 0, and then we come back to sweep right. If at any time the command is sent to disable, we immediately jump to our off position, and we keep the servo in whatever position it was left in. So that's our state machine. Pretty simple, but it does use timers, and we're going to timing, and I will explain that as we start to build it. So as I did before, I'm going to want to take this state machine and I'm going to want to put it on my block diagram. So I'm going to grab the Windows snipping tool. And I'm going to just copy this image. And I'm going to right click and say copy and then close it. And then I'm going to minimize this. And then we're going to go here to our actuator loop for our agitator. Control E to bring up our block diagram. And then up here I'm going to paste, Control V, paste my state machine so I can come back and refer to it. Okay, so if we go back to our time task where the current actuator code is, we're going to go to my project and open time tasks or periodic tasks. And remember, what we're doing is we're replacing all this code here with our state machine code. But we still need to set our angle for servo, so we need to open the servo actuator. And if we go to begin, see, here's our agitator, runs on PWM number 6. So we'll need to put that in our code for our actuator. So that'll go here, our PWM 6 or an open will go here, and our actual setting, the position of our actuator will go here, if you remember how to do that. So another thing that we need to add to our cluster here is a start time and a start position. The template already provides a start time because we will probably use this a lot when we're doing timers, but we need to create a start position here. So that start position, I'm just going to copy just any double and call this start position. And we'll add this to our cluster. So let's look at our calculations and see if there's any other items that we need to add to our cluster. So we see up here we have degrees to move. So we'll add that to our cluster. We have sweep speed. We'll add that to our cluster. And agitator speed. So let's add those 3 items. So before we start building this, one of the other things that I want to talk about that we need to think about is when we have calculations like this, we need to decide where in our program to put these. So we have 2 locations. One would be here in the repeated update calculation area, and these are for calculations that are done almost every iteration. Doesn't have to be done, you don't need them for every iteration like shutdown or startup, but they should be calculations that that a lot of the actions or the states depend on, that these calculations are continuously happening. So if you're doing PID control or feedback control, a lot of times you'll put the calculations here in the repeated calculations because you want those calculations done every loop. And then the other place that you could do these calculations is in one of our action states, our action cases. And that would be a calculation that you typically would only do in a specific state when that action is called. So for this instance, I'm going to do these calculations only here when we do decrease or we do increase position. I'm going to do these calculations. So I'm going to do these calculations here in an action case, but later we will actually do calculations here in the repeated tasks. But you need to think about where your calculations need to go when you have them when you're doing calculations in the state machine. Okay, some other things we need to think about is what is our input data going to be. So if we go back to our time tasks, periodic tasks, where the agitator code is written, we'll see that we're using here a network variable, network table. variable. This is data that comes from a dashboard, and we'll talk about dashboards later, but it's basically coming from the driver station, setting our agitator sweep speed, and then you'll see that we store that agitator sweep speed here in a global variable. So we will also need to do this code in ours. We're going to read from our dashboard what the agitator sweep speed is, and we're going to write that to a global. And then this code is actually similar to what we're going to write with our state machine. Hopefully it'll be a little more understandable than this string together code. All right. Other things we need to think about, states. We also need to create in our template here, we need to use the command actuator, and we need to create an enum that says enable and disable. So we want to be able to enable and disable the sweep. Those are the only external inputs aside from the sweep speed that will come into here. So we need to bring in a command, and we need to bring in an agitator speed. And between those two items, that will control our agitator. Okay, so I'm going to begin building this. I'm going to put the real-time build of this code in a separate video. I'm going to speed this video up in this so we can get to the ball shooter. We can explain the agitator, and then we'll move on to the ball shooter, and I'll create a step-by-step video of that as well. Okay, so I finished building the state machine, and let's review all the different steps that I went through. So I opened the servo here and save the reference. You'll see that I made a little bit of a mistake here. I swapped the agitator reference in the command actuator data. Yours was probably reversed if you did it correctly, but it doesn't really matter as long as you have it in the cluster and you want to bundle it correctly. And then we go to our read input data. So we read our command actuator agitator data, and I had to create an enum for that. So let's see, if I open the front panel, you'll see I have an enum that's disable and enable according to our state machine, and one item, and I've named it command actuator agitator data to following our naming convention rules. And I'm also reading from my network table variable here, like they were doing in the other code, and we save it to our agitator speed, and our agitator speed is in sweeps per second. So actually let's add that so we remember the units. Sweeps per per second. Get a little bit longer, bigger, but I'm going to control drag here and give myself a little more space. And then I'm going to clean up these wires. All right, and then the next section, we didn't add any additional calculations. We decided to do our calculations in our action cases. And then we come to our states, and we start with our startup state. Our startup state, according to our state machine, should just go directly to off. And it does, with no action. Our off state looks at our command, and either we're enabled or disabled. If we're disabled, we come back to the off state, and if we're enabled, we go to the sweep right state, and we save our time and save our position. And so if we are disabled, if we are enabled, we go to our sweep right state, save our time, save our start position. Our next state is our sweep right state. Sweep right state, we look for command enable, and our position is less than 70. We do an increase our position and come back to sweep right. So if we are enable and our position is less than 170, true, we sweep right and increase position. If our command is enabled and we are greater than or equal to 170, we will go to sweep left state, save our start time, save our start position. And then finally our sweep left, we're looking for command enabled. If we are less than, if our position is less than 0 or greater than 0, we decrease our position. True, greater than 0. Stay in the sweep left state, decrease position. And if we are not greater than 0, equal to 0, or less than 0, we go to the sweep right state, save our start time, and save our start position. All right, and then we do our actions. So our reset time and reset all. I decided to take all the code out of reset all because there's not really a reset. We don't want to move our servo. We just want to always leave our servo exactly where it is. We don't want to reset it to 0 or anything like that. So we're going to, for save start time, we just take our current time and write it to start time. For save our start position, we write our current agitator position and write that to start position. For increasing our position, we try and follow this formula here. So our sweep speed is equal to agitator speed times 170. So agitator speed times 170 equals our sweep speed. Our degrees to move is our sweep speed times our current time minus our start time. So here's our current time minus our start time. That should give us the time elapsed. And then we multiply that by our sweep speed to get our degrees that we need to move. And then we add our degrees to move to our start position. And that will give us the total from our start position to the degrees to move, what our new agitator position should be. And our decrease position is exactly the same, except we subtract from our start position what our degrees to move should be to get our new agitator position. And then finally we write our outputs. So we write our agitator, actuator, this should be agitator position to our front panel so we can view it, and our cycle time. And here we are bringing our agitator position and we are putting it into a range function. So the range function, what it does, Control H, is it forces it to be in range. So we don't want to set our servo angle greater than or less than 0 or greater than 170. So we're going to limit it to being 170. So if by chance the agitator position when we calculate it over here goes negative or goes greater than 170, we're going to force it to 170. And we're actually going to then we're going to come back and we're going to rewrite our agitator position to what we set it to, not to what we can after we've calculated it, so that it always stays between 0 and 170. And then the final thing I forgot to do is create a header or template for my library. So let's go Control Shift E. Let's go to our library. We're going to right click in here and go back to properties, and we're going to build an icon, a unique icon just for our agitator. And I'm going to make that my header for all my VIs in this library. Click OK, click yes, and then see now all my VIs that are in that library change their headers to agitator. Okay, so we're ready to put our agitator loop into our main VI. All right, and then I need to get rid of all the actuator loop code so we can get rid of. Okay, so we've gotten rid of all the agitator code that was previously there and replaced it with our own. All right, so now let's go to teleop. We need to bring in our command for our agitator. So we're going to bring in our command cluster for our agitator. So I'm going to go select VI. I'm going to go to System Agitator, and I'm going to be the command, the cluster, the command actuator data. Bring that in. I'm double click on it, and then I'm going to do an unbundle by name. And there's my agitator command, and now I need the global command, the variable, the command actuator agitator data, the global. So I'm going to go select that. Here's my global command actuator data. All right, and so I have the option to disable or enable my agitator. All right, so I'm deciding that I want to make this a toggle. So I want to push a button and have it turn on, and I want to push a button and have it turn off. But I don't want it to be a very button that I use a lot. So I have the back and the start buttons that aren't near my thumbs or whatever. So I'm only going to push them very periodically. So I'm going to use the toggle up here, and I'm going to unbundle from my toggle array. And I'm going to copy this, and I'm going to use my back button, which is just a small little black button next to the POV on my gamepad. It's called the center pad back. I'm going to unbundle that one. And if it is true, so I could use a case structure here, or I could use a select. So let's use a case structure. All right, so if my back button toggle, remember I'm using a toggle, is true, I want to enable the agitator. And if my toggle button is false, I want to disable the agitator. Okay, so I think we have programmed everything. So let's see if it will run. So you can see the balls are pretty still. Can't exactly see the agitator, so I'm going to now push my ups. I need to go to my driver station and enable. Okay, agitator's not moving, and let's see, can I drive forward? So I can drive forward, so my robot's working. Now I'm going to push my back button. You should see the agitator start moving the balls around. And now our code is working. And if I push the back button again, the agitator should stop. And the ball should settle down. Okay, now the ball shooter works. Let's open our Statemachine while it's running and kind of follow along and see what it's doing. So I'm going to go back here and I'm going to push my back button so my agitator starts, and then I'm going to go here to my agitator loop, and I'm going to look at the front panel, and I see that my agitator position is not registering. So let's debug that. So I'm going to go back to my block diagram, and I'm going to put a probe here. I know my agitator position is here. I know my agitator is moving, so let's put a probe here. And my probe says that my agitator is moving up and moving down. Okay. But I look here, my agitator position indicator is wired to this actuator output double, not my actuator position. So that's why my indicator is not following the angle of my agitator servo. So let's go ahead and fix that. And you can go back to robot main. Press my start button. Oh, my agitator's already running. And now let's look at our front panel. Control E. There, we see their agitators going up and down, just as we expected to. So we can do some more probing. We can probe in here on our state, see what's our state. Sweep right, sweep left, sweep right, sweep left. We can probe and see how fast are we sweeping. We're sweeping 1 sweep per second. That's pretty quick. So this will conclude our video for building the actuator agitator loop. I will be creating a separate demo video that will show my step-by-step process of building this in real time. It will also include any mistakes or issues that I ran into while building it. I wasn't able to get to the ball shooter in this video, and I will be coming back to that in the next demo video. Previously in this video, I stated that we would also try and build the ball shooter actuator loop. I'm going to move that to the next demo so I have more time. And as a reminder, this bit.ly link here will take you to all the demo code that I've been creating for these videos. So we will see you next video, and thanks for watching.